There's this one data structure that, on the surface, seems almost too simple to be useful. But with just two tiny tweaks, it transforms into one of the fastest tools in all of computer science, able to track millions of connections in the blink of an eye. So today, let's dive into the astonishing world of disjoint sets. Okay, picture this. You're in charge of a massive network. Could be anything, a social network, a computer grid, maybe even a complex circuit board. You've got a million different things, and you constantly need to group them together and then check. Hey, are these two things in the same group? How on earth do you do that? Like right now, instantly.
All right, let's make this real. Imagine all these dots are islands, and the lines are bridges connecting them. We need a system that can instantly answer questions like, are island A and D connected somehow? Or maybe, if we build a new bridge from E to F, does that suddenly mean G is connected to F too? This, right here, is exactly the kind of problem disjoint sets were born to solve.
So what is this magic tool? Well, it's officially called a disjoint set data structure, but you'll also hear it called union find, which is a great name. Let's break down what it's all about.
The whole idea really just boils down to the name. Disjoint just means separate. This structure is all about managing groups of items, but with one super simple, unbreakable rule. No item can ever be in more than one group at the same time. Think back to our islands. Every island can only belong to one archipelago. That's it. And here's the cool part. You only need 3 basic moves to make it all work. First, make set. That just creates a brand new group with a single item in it. Then there's find set, which is like asking, hey, who's the leader of the group this item belongs to? And finally, union. This one's easy. It just merges 2 separate groups into one big one. All right, so how would you even begin to build this thing? Well, the first idea that probably comes to mind is to use something we all know, a linked list. But as we're about to see, this simple approach, it has a pretty fatal flaw.
So using linked lists, a union operation looks super easy. To merge 2 sets, you just take the end of one list and point it to the beginning of the other. Done. Seems simple enough, right? Well, there's a catch. Every single item in the list needs a pointer that goes back to the leader of the group. And that's where this whole idea just completely falls apart.
And this is the problem. When we merge 2 lists, we literally have to go through every single item in the list we just attached and update its leader pointer to the new leader. If that list has 1,000 items, or 1,000,000, that update process becomes painfully slow. And this is the absolute kicker. If we get unlucky and keep appending really long lists to short ones, the time it takes just explodes. For n elements, it can take something like n squared time. For 1,000,000 items, that's 1,000,000,000,000 operations. Yeah, that's not instant. That's more like, go grab a coffee, come back next year, and maybe it'll be done. This approach, it's a complete non-starter.
Okay, so linked lists, total dead end. We need a much smarter approach. So, instead of a flat list, what if we organized each set as a tree? A whole forest of them.
Now, this is a game changer. Remember, with lists, a union meant we might have to update hundreds or thousands of pointers. With a forest of trees, a union means we only have to update one. Just one pointer. You make the root of one tree point to the root of the other, and that's it. Huge improvement. But wait, there's always a catch, isn't there? If we're not careful, we could accidentally build a tree that's really tall and skinny. Basically, a linked list wearing a clever disguise. And suddenly, we're pretty much right back where we started. A find operation could take forever, just climbing up that long chain. So we've just traded one problem for another.
So are we stuck? Nope, not even close, because this is where the real magic happens. We can fix this whole skinny tree problem with 2 incredibly simple but unbelievably powerful little tricks.
The first trick is called union by rank. The whole goal here is just to keep our trees from getting tall and spindly. We want them short and bushy. So we keep track of a rank for each tree, which is kind of like its height. And when we merge 2 trees, the rule is always the same. Attach the shorter tree to the root of the taller tree. This one simple rule stops those long, skinny chains from ever forming.
And the logic here is, well, it's dead simple. You find the leader of each tree, you compare their ranks, and you just make the shorter one a child of the taller one. And that's literally it. It's a simple little choice that pays off big time by keeping our trees as flat as possible, which means our find operations stay super fast.
Okay, if you thought that was cool, the second trick is even better. It's called path compression. This one happens when you're doing a find set. As you climb up the tree to find the root, on your way back down, you do something absolutely brilliant. You take every single node you just visited and you rewire it to point directly to the root.
So think of it like this. The very first person to ask, who's the leader, might have a bit of a long journey up the tree. But by doing that, they create a superhighway for everyone else. Any future search from any of those nodes becomes an instant one-hop trip straight to the root. It just completely flattens the tree over time. It's awesome. So let's recap. We started with a really slow n-squared solution. We moved to trees, which were better, but they had a big flaw. Now we've added two simple heuristics, union by rank and path compression. So what happens when you put these two simple ideas together? Well, the result is, honestly, it's kind of hard to believe.
The math shows that the total time for a whole bunch of operations is on the order of m times alpha of n, which leads to the obvious question, what in the world is alpha of n?
So alpha of n is the inverse of this wild thing called the Ackermann function. Now, you don't need to get lost in the math here. Just remember this one thing. The Ackermann function grows faster than anything you can possibly imagine. So its inverse, alpha of n, grows so ridiculously slowly that it's practically standing still. And this is the punchline. For any number n that you could possibly work with, I mean, a number bigger than the number of atoms in the universe, the value of alpha of n will not get bigger than 4. So in the real world, this means the running time is basically linear. Each operation is, for all practical purposes, constant time. I mean, going from n squared to basically constant time, that is an absolutely mind-blowing improvement.
And there you have it. A simple problem, a few smart ideas with some hidden traps, and then two incredibly simple tricks that make the whole thing work with almost magical speed. It's just a perfect example of how, in computer science, a tiny bit of clever thinking can lead to these absolutely staggering leaps in performance. It really makes you wonder, right? What massive problem out there are you going to solve with it?